Hello, and welcome to another wonderful episode of the New York City Category Theory Seminar. It's March 29th, 2023. Tonight we have Jim Otto, whose camera doesn't work, whatever, but his sharing screen works, and he's going to be talking about PTime, a bounded arrows category, and entailments. Jim, we have a little thing in tradition that you say something about yourself. I know you got your PhD in McGill. Where did you do your undergraduate, and what city are you in now?
I'm outside of Chicago now in a place called Bellantoni.
Uh,
And yeah, my original undergraduate was at UC Berkeley, but that was in math, but I also did computer science at Cal State East Bay. And then I got a master's degree in math at Berkeley, and I also got a master's degree in electrical engineering at Santa Clara University. And then with my advisor, Michael Barr, who's showed here, got a PhD at McGill.
Very nice. Okay, Jim, take it away.
Oh, okay. Okay, so at the suggestion of Nissan, I'm starting with he suggested the word doctrine, but actually two Bill Levere words are key to this revisitation of characterizing the p-time functions that was in my thesis. Yeah, and that, so there's, so the Bill Levere idea of a doctrine is basically a theory of theories, and there's more than one version. I'm not particularly close to the Max Kelly version. Mine is pretty close to what's in Cook and Reyes. And there's some sort of unaesthetic aspects of the way I do doctrines, and that you might want them to be higher dimensional so that you can somehow not get around choosing structure. But mine are one-dimensional categories whose objects are small categories, and the structure is chosen. And even though it's not aesthetic to choose the structure, the advantage of doing that is that then they end up either being locally finitely presentable categories or locally finitely multi-presentable categories. And so,
They're just a group of category. They're a collection of categories with a particular structure. That's
yeah, so like a Coke-Ray's example would be like a like the doctrine of finite product categories, or the doctrine of finite limit categories, or the doctrine of toposes.
okay. Okay, good.
Yeah, so the doctrines I'll be considering are the a PR doctrine for primitive recursion, which is a way of looking at work of Leopoldo Ramon, and then the p-time doctrine for doing the functions that are computable in polynomial time. And then another doctrine that I'll just consider just very briefly is the CC tilde doctrine, where it's toposes with numbers, choice, and precisely two truth values. And that's an interesting doctrine because that doesn't get you all the way to Zumirlo set theory with choice, but it gets you very close. And it's it's not Zumillo-Franco because I'm not worrying about replacement.
Well, two value is that
Two
two
truth
val
values. So
is
like
that
when you
Boolean valued? Is that the same thing as Boolean valued?
that's stronger because Boolean value could have more than two truth values. Is that when you have an arrow from 1 to omega, it's either true or false. No other, it's exactly those two. If you choice would already implies Boolean, but so in fact, it's kind of interesting to do toposes, numbers, and choice, because then you can choose structure and make it locally finitely presentable. And then there's an initial one. but it probably has a really massive number of truth values, and then you probably use what is it? That's escaping me. There's a huge number of ways to cut it down to having two truth values. So that's something I will need to look at, but I'm putting it up here because it's not obvious that a doctrine is locally finitely presentable. It could be locally finitely multi-presentable, and that the issue there is when you're locally finitely presentable, you have an initial category. For example, in the locally finitely presentable category of small commutative rings, the integers are the initial ring. Whereas if you have the locally finitely multi-presentable category of small fields, instead you have an initial family of fields, the rationals and then the integers modulo a prime. So it's a pretty big distinction. So if I have enough time at the end of the talk, I will talk about presenting doctrines using either entailments or multi-entailments. And the neat thing about doing that is that when you can present by entailments, not only is it locally finitely presentable, but you have a systematic way to construct the initial category using answer over deduction fractions. Whereas when it's only the multi-presentable, then you instead have an initial family of categories. And then putting some important stuff up front, my idea of entailments comes out of an idea of structures that was inspired by Mackay's sketches as well as by Presheep's. And then the multi-entailments are the entailments are closely connected. Yeah, they actually, I said, yeah, this still needs a revision here. As I said, my entailments are finitely presentable categories, but it's actually, they are the finite presentations of some arrows between structures. Whereas the multi-entailments, when they present instead finite discrete base cones of these entailments, where the idea is each leg is an alternative, and then you can model entailments and multi-entailments using notions of orthogonality or cone orthogonality, which is in the Atomic and Riziki book on accessible categories.
Okay, but this whole entailments, you said you're gonna leave out.
No, not necessarily leave out,
but maybe later.
Yeah, at the end.
Okay.
Yeah, so that's how I actually know that in these first two doctrines I have initial categories and that can actually construct them, but I won't actually be well. So it's more like it's more like you assume that there is an initial category, and actually you can sort of figure out what it is, although it's nice to be able to systematically know what it is and then know what various maps from the initial category to other categories are. But anyway, so that's the keyword doctrines. Now for the keyword for comprehensions, and Joachim Diaz-Biles has looked at my thesis and emphasized how important the idea of comprehension is used in cutting down recursion to complexity. And then I should mention that I learned of comprehensions from Duško Pavlović when I was at McGill. And yeah, and then when you write down the functors and natural transformations for a two comprehension, it looks like kind of a mess, but actually the whole thing comes out of looking at the ordinal 2 as a category, and then looking at the endofunctors and natural transformations between those on the ordinal 2. And then briefly mentioned in my thesis, I actually, besides 2 comprehensions, consider the notions of 3 comprehensions and V comprehensions.
Okay, Jim, you've made a lot of connections here, but you don't tell us what comprehensions are. I mean, I know what it is in terms of set theory. I don't know what it is in terms of category theory.
Okay, so
You
yeah,
pass
so
me.
here's what a 2 comprehension is. It's these functors using Michael Bar notation. Yeah, this is notations for co-triple and triple, as in Michael Barr's first book, or one of his books, and it's specified by these equations on the functors, and then these equations on the natural transformations. And I say it looks like a mess, but it's actually just the actions on the ordinal 2.
So comprehension is adjoint functors from the category to itself.
Well, yeah, actually they're adjoint, and and this is not only a co-triple, it's idempotent. And same thing for this triple. And
by triple, you mean monad/comonad in?
Yeah.
Okay, so it's a pair of a idempotent monad and idempotent comonad that have a certain sort of interaction with one another.
Yeah, so num here is the category where the objects are finite products of the natural numbers. Right, so the num is a subcategory of the category of small sets, where the objects are finite products of numbers, and the arrows are the functions between them. And then num 2 is the arrow the category of arrows in here, and then of course the arrows in here are the commuting triangles in here. And here you have a very concrete, because you have a functor where you just look at the bottom of an arrow. The thing of the arrows is going down, and so D0 looks at the bottom of the arrow. S0 takes a set and just makes it into an identity arrow, and then D1 takes an arrow and just looks at where it's top.
Jim, what does a comprehension have to do with the doctrine? What's the relationship there?
Oh, in the doctrine, so the PTime doctrine is going to consist of small categories with chosen structure finite products, 2 comprehensions respecting the finite products, base 2 flat recursion and base 2 safe recursion. And the 2 comprehensions are used in talking about, and actually it's used in defining the safe recursion.
Okay, so you need this notion of comprehension in order to define your doctrines. Is that it?
It's part of defining the doctrine. It's part of the structure in the doctrine. It's part of how this doctrine differs from the PR doctrine.
Okay, so can you show us what the comprehension for the PR doctrine is?
The PR doctrine doesn't have a comprehension. The PR doctrine consists of small categories with chosen structure finite products and a product stable natural numbers objects.
Right. So given that, you can define primitive recursion. Okay. So now, so fine. So now you want to take that and you want to. So this comprehension is very important for the rest of your talk, right?
Yeah, as I said, the 2 really important words are doctrine and comprehension. Yes.
Okay. So can you give us an intuition of what this comprehension does for you? That makes it PTime. Mike, I mean, you were the first one to define these comprehensions.
Oh,
Hold on.
to understand the Bellantoni. Oh yeah, let me go through the genealogy. Let me back up and go through the genealogy of this characterization.
Yeah, maybe we're jumping around a bit too much. I mean, I do want to understand the comprehension stuff a bit more, but maybe once we follow through on the talk sort of prescribed order, that'll get us there.
Well,
yeah.
I don't mind jumping around.
And there was the example with the numbers in there that.
Yeah, so the genealogy kind of has a category tract and it has a non-category track. In the non-category track, back in 1965, Cobham put explicit bounds on primitive recursion and used base 2 numbers in order to cut down primitive recursion to the PTime functions. And that was kind of neat, except it was annoying to have explicit polynomial bounds on your recursion. And Bellantoni-Cook rather magically got rid of those explicit bounds, so what Daniel Levant would say that they became implicit. And they did that by having in Levant's terminology, 2 tiers of numbers. In the Bellantoni-Cook, they talk about, well, actually, they talk about safe and normal numbers, but I'm sort of saying safe and unsafe for tier 0 and tier 1. And getting these what the comprehension does is it takes you from the flat recursion, which is mostly in tier 0, and gets you the tier 1 numbers that you can then do the safe recursion. So here's the idea in that num2 and the numeric arrow, num2, which is starting numeric arrows category. The tier 0 numbers are just the arrow where you collapse everything down to a terminal, to a singleton set, whereas the tier 1 numbers are this. And then because what the way I came up with the idea of my thesis is I looked at a preprint that I got early on of the Bellantoni-Cook result, and I noticed that they had an unusual way of composing their functions, and what it was is just the num2 composition. It's just composing the commuting squares, where you have anyway, so to get back to this thing, you had the explicit bounds, implicit bounds, Leopoldo Ramon having using an initial boils down to initial category and a doctrine to do the characterization, and then I sort of boiled these 2 things together. Okay, so to
1 second, Roman's paper is just about PR, not about PTime, right?
Yeah.
So your thing was the combination of those 2 things. Okay, fine.
Yeah, basically. Oh yeah, this is basically a kind of a commuting square here. Well, actually, it's not so much. It's actually more of a cocone. Yeah. So anyway, the primitive recursion, you have this doctrine. So of small categories with chosen structure, finite products, and product stable natural numbers. And there's entailments for that doctrine, and they're actually toward the end of this PDF, although the explanation of why those entailments are what they are is in this paper that's on ResearchGate. So anyway, then Yeah, so you have an initial category in this doctrine. Then you have this num category where the objects that are finite products, the natural numbers and the arrows are the functions between those objects. And so because this is an initial category, there's a unique functor within the doctrine from I to num. And my reading of what Leopoldo-Ramon showed is that if you look at the image here, the functions over here that come from here, that are in the image of C, so that they actually have in an I arrow represents them, those are precisely the primitive recursive functions. Yeah, and so yeah, there's some technicalities here that I will gloss over unless someone asks me. Okay, so I'm assuming people know what finite products are. So it means to talk about base one natural numbers and product stability. So I think people probably know what a base one natural number object is.
I know what a natural number object is. What's a base one natural number object?
It's a natural number object. The point is there's also base two ones.
Okay.
What is so I guess you can tell us the distinction between them or the extra.
Is base one a piano natural?
Yeah, it's just in set. It's just zero is you include the singleton where the singleton is zero, and then you have a successor by adding one. And categorically, the point is you have this kind of shape, and it's initial among these shapes, where the arrows between these shapes are these commuting squares.
Okay, we know what a base one we know what a natural number object is. Okay.
Okay.
Now what's a base two natural number object?
You have two successors, and then in a set, zero is the same, but now your first successor is multiplying by 2 and adding 1, and the other is multiplying by 2 and adding 2. So again, when you look at a numeral, you put a string, instead of just S's and T's applied to the 0. And what that will end up doing is, instead of just giving you a number that's just a string of ones, and then the number of ones is the number, instead you have a string of zeros and ones, and these are dyadic base two numbers rather than the usual binary, which uses the digits 0 and 1, which then leads to leading zero issues that I get rid of by doing this. So it is just a string of ones and twos.
So you've internalized the notion of digit representation of the number in your category.
Now,
yeah,
in many common categories, right, it must be the case that these two objects are equivalent, right? Like
in the PR category, they're equivalent.
Yeah, or like just in
Whereas
set, right?
once we have the two comprehension, they become quite different. From base one, we end up, according to Steve Bellantoni's thesis, the functions that are computable using linear space. And that even goes, whereas when you do base two, instead you end up the functions computable in PTime. So the base makes a huge difference once you cut things down using a two comprehension.
But yeah, but my question is, like in set or something, right? They would like the category set.
The set categories of small sets is in the PR doctrine. So yes.
Okay, gotcha. All right.
Thanks. I mean, you can in fact do a Kalmar elementary doctrine, and it's already true there.
Ray, you want to say again what you mean by what did you say?
Well, just that he internalized the notion of digit representation, right? Because we have these two successors which correspond to adding a digit 1 and a digit 0.
Yeah, so you have your base 2 and then your digits. Yeah.
Okay,
So,
so
That's really interesting. That is to me, yeah.
well, actually, it's crucial for the complete, because in characterizing the p-time, there's two parts. There's completeness, that you got everything, and there's soundness, that you didn't get too much. And this is crucial for the completeness, because then once you have these things, you're really close to machines where you have these stacks of these digits. And if you have a Turing machine, you know, you only need you can code up all your stuff on the tapes using digits 1 and 0 or 1 and 2, and then you can split the tapes into two stacks, and then you have these multi-stack machines. So the other thing that I'm missing in the PR doctrine is you either need a base 1 or a base 2 natural numbers object, but then you need product stability. And the nice way to do that is to use the Lambert-Scott polynomial categories, where in the slice category, you have the full subcategory of the left projections. And you...
I'm sorry, could you go back for a second?
Mm-hmm.
I understand that a Turing machine is equivalent to a finite automaton with two stacks.
Well,
but I
don't know that you might need three stacks.
How do you get?
Two stacks, because that makes one tape. That's true.
Right.
But it's convenient for me to have finite number of stacks.
Okay.
And it's actually, when I was characterizing linear time in my thesis, I actually needed it to be multi-tape machines. Because if you only have the one tape, that probably doesn't give you all the linear time functions.
Okay, but explain to me why having your numbers as binary gives you a stack. How do you get from base 2 natural number?
Oh, I see. How do I get a stack? When you have a tape, you know, you're moving along the tape, you can sort of take where the tape head is, and then you can make that the split. And then if you want to move something along, if you want to move the tape, you'll pop off one stack and push it onto the other.
Right. That's showing that a Turing machine and two stacks are needed. But how does it come from your base 2 natural number object?
Because
how do you do this inside the category?
Okay, so that gets to the idea of flat recursion. So when we do have the 2 comprehension, we can then, on a category, so I add that functor t, so we can take the objects that are killed by t and take the full subcategory of those things. You know, for example, in num, which is our starting model, you even have an isomorphism, because you're looking at the things that get the arrows that get killed when they go down. And so any object can be put into that form. So now flat recursion says that you have a sum cocone like this. So we can get one like that by, again, doing these things. But saying it's a sum cocone means that if I had another cocone here, or actually, another cocone, so I have arrows coming out, that I would then get an arrow here. And what that is saying is if I have a stack of ones and twos here, I try to pop it. If I can't, then I use this alternative. If it's a 1, then I use this alternative. If it's a 2, I use this alternative. So out of the idea of the base 2 flat recursion, I basically get a multi-stack machine, because I have this idea, because I can push digits 1 and push digits 2, and then I can do this 3-way conditional on when I try to pop. And the only other instruction I need is halt, and the pop just needs to, or push needs to say, which stack I'm pushing onto and which digit I'm pushing, and then where I go to after what instruction I go to after I do that. Whereas the popping, but then I look at what I popped, and based on that determines which of 3 possible instructions I go to next, and then that's basically all that you need for the machine. And that's the only other thing to get the completeness result for PTime is to be able to run machines like that long enough.
I'm sorry, let's talk classical recursion theory. A primitive recursive function is PTime if it can be run on a Turing machine? No, I mean...
Yeah, well, I'd say on a multi-tape Turing, well, on a Turing machine, and I guess the number of tapes doesn't matter.
Right.
And I guess actually but it can be finite number of tapes, and that's what I want, because I want finite number of stacks.
Okay.
Because in that category num, my objects are finite products of natural number objects. So I'm looking at it as being a finite collection of stacks.
Yeah, I'm just a little bit confused. Primitive recursive functions are computable, are all computable.
Oh yeah.
Right. So now you're saying you want primitive recursive functions that are computable on a multi-stack.
Yeah, and the other thing is, the thing that makes it not just primitive recursion is that it can't take longer than, well, yeah, so time is the number of instructions executed. Right. And you're saying that if I look at the number of input digits and I take some polynomial in those, that'll give me a bound on how many instructions I have to run through.
So that's the flatness condition? What is that?
The flatness condition allows me to define the machine, and then the safe recursion actually allows me to run the machine in a loop and to run it for long enough.
So it's inside the safe recursion that you've encoded the polynomial time?
Characterize the polynomial time. I mean, the Bellantoni-Cook magic is that the polynomials just come, that they're not, you don't have to have them there to begin with.
Right. So what do they come from?
I don't think you said yet what safe recursion is.
No, I haven't.
Oh, okay. So
yeah, so I pretty much said what flat recursion was when I was just talking about essentially one stack, but I need to have multiple stacks, so I need a product stability again, and that's just that when I have an object and I use the product endofunctor, that it should take this sum cocone to a sum cocone, and then that's the finite number of stack flat recursion. And I should mention that, well, that flat recursion, the terminology was from Daniel Levant's reading of Bellantoni-Cook, and then it was Robin Koch who told me about the observation that was just saying that this is a sum cocone. Okay, and we're doing this in tier 0. So now in safe recursion, I'm going to take that tier 0 natural number object, and I'm going to make it tier 1 by applying the G endofunctor. You know, so in num 2, this would be n going, or natural numbers going down to 1. When I apply this, it becomes natural numbers by identity going down to natural numbers. And yeah, so safe recursion, it it starts with the idea of that base 2 primitive recursion, except that now there's some limitations that my iteration vector has to be tier 0. In the Bellantoni-Cook terminology, it has to be safe. And then, yeah, so what's going on here is, and again, I'm using this polynomial category to have parameters where the parameter can be a hybrid of tier 0 and tier 1. And so in this setup, this is going to be controlling how long the iterations can go on, because so I'm using up digits when I go along here. So I use up a digit and I apply an iteration function. But the iteration function, the vector that it can actually work on read write is tier 0, whereas the parameters can not necessarily be. Yeah, they could be tier 0 and tier 1, and in fact, at the point of C, there might even be other possibilities, but it can look at them read only, and that ends up to be crucial for defining things. And I think I will skip way down. Yeah, so the part of how I'm able to run the machine long enough is that the function going into that GN has to be big enough. And the crucial thing to there is an idea of smash, which is the base 2 analog of base 1 multiplication. So base 1 addition becomes base 2 concatenation by using safe recursion to solve this equation. And here, these things, because of the definition of safe recursion, these are tier 1, or rather these things are tier 1, but Y is necessarily tier 0. And so when you solve this with safe recursion, what you're doing is you're concatenating the digits of Y and N together. That's what you're doing there. An important thing here is that the parameters I used here are safe. So that concatenation, this input is unsafe, but this one is safe. So that allows me to use it in another safe recursion. So that allows me to define smash. But at this point, all of its inputs are unsafe. So unlike in the primitive recursion, I can't go farther. In primitive recursion, I could iterate multiplication and get exponential, which would be fatal for PTime, but I can't do that here because there's no safe inputs.
So to the question that came earlier, it sounds like what you're saying is this inability to iterate the multiplication is what basically allows you to have polynomials without having to put in polynomials explicitly.
Smash is one side of it. It'll because when you look at what's happening to the digits here, you can start building up functions that will have the appropriate growth thing, where you put in so many digits and then you'll get a number of digits out in any positive coefficient or any negative coefficient polynomial. You can blow it up that way. Because essentially you have in terms of numbers of digits, you have the addition from concatenation, you have the multiplication from smash. And so, yeah, in terms of completeness, that gives you the polynomials. Yeah, so let me complete the sketch of the completeness argument. And that was that I do take a Turing machine and split the tapes into stacks. And Weirach has machines that are similar to these multi-stack machines. And yeah, then using smash and concatenation, you can build up functions that will then run the safe recursion long enough to run the multi-stack machine for polynomial time. So that's the sketch of the completeness. The soundness is harder, and the polynomial, we need to now make the polynomials explicit where they're so far in the PTime doctrine, they're not there on the surface, they're implicit. So that's where the idea of this bounded arrows category comes in, is that inside this this big numeric arrow category, I want this category B where the objects are now not any arrows between products and numbers, but only ones that are products of the tier 0 numbers and the tier 1 numbers. And then necessarily, because this is a subcategory of num2, this is what the arrows look like. So there'll be a part that just works on tier 1, and then there'll be a part that takes tier 1 and tier 2 things and comes out with tier 0. And then I have two ways of putting a metric on one of these vectors. So if especially with the type 1 or the tier 1 vectors, I want all of their digits. So this is the number of digits in just one stack, and then this is adding up all the stacks. Whereas in tier 0, I want the alternative idea where I just look at the maximal number of digits in the vector of stacks. And then on these set functions that are forming the P arrow or the B arrow, I want to put on these explicit bounds. That I want everything to be running in polynomial time. But then the Bellantoni-Cook magic is to have this output bound when I'm going to tier 0, that it should be this, the maximal number of digits should involve a polynomial from the tier 1 stacks, but it should only be the maximal number of digits you're just adding on the maximal number of digits in the tier 0 stack. So then, so actually the heavy lifting is to show that B actually is a category and that it's in the PTime doctrine. Once you can do that, then you necessarily have this factoring. And then, then I forgot to say what the characterization I'm going for is. I'm looking at the arrows in here as going down. And so the arrows here are commuting squares, and I want to look at their bottoms. And then when the bottom is in the image of this, when the square is in the image of this thing, then its bottom runs through precisely the PTime functions. The top is auxiliary, and I'm not characterizing it at all tightly. So yeah, okay. So the thing that actually probably needs more polishing is to actually show that B inclusion really is in the PTime doctrine, although that's what that's doing is it's repackaging an inductive argument over the I arrows and instead getting the fact that I is initial, just instead getting out of that it is initial, so that you're sort of hiding an inductive argument. So the B inclusion, and I need to actually straighten this notation out more, but I mentioned the multi-stack machines. You know, we just have these push instruction, pop instruction, halt instruction. In composition, then you start to see the importance of this tighter than polynomial bound, that when you look at this composition, you get this kind of thing where the y's are not blowing up. The x's are still making things blow up polynomially, but the y is very controlled. And then the crucial thing then in safe recursion in the loop, what you're doing is you're starting with the initialization, and then you're applying your iteration functions to the iteration vector. So you're building up a bunch of composites or compositions. And then the thing about that is that you have a bound on what's happening to the iteration vector, that it's you have, because you start off with what you get from the initialization, but then as you it's because you have this bound on the y as you go through, the compositions are just multiplying the final stage by the number of iterations through the loop, and x isn't changing. It's effectively read-only. And then because you have this control over what's happening to the iteration vector, that means that as you actually do the safe recursion loop, you actually are only taking polynomial time because you have this control over the iteration vector. So that's actually the most crucial part of this whole thing. And now there's not much time left. Are there questions? Because I'm not hearing chatter at this point.
There's some questions for after the recording, but
okay.
But you can finish up. It's, you know, there'll be some. You finish up.
Okay.
Oh, go back to the references. Who's that? AH you were saying?
That's the. So a lot of the references are to writings that I have that are at ResearchGate, and I'm there as Jim Otto.
Okay.
You know, so like AH1 is entailments for the. So I want to try to really quickly talk about entailments, because sort of that's the big machine that I didn't have until after I wrote my thesis. So I tried to do things that were sort of trying to intuit toward that idea, but I wasn't there yet. So that was kind of ugly.
So Jim, you finished?
No, I'm not finished.
Oh, okay.
I have, I want to wave my hands quickly at the idea of entailments.
Yeah, could you define entailments?
I'm going to do that right now. Yeah,
okay,
and
great.
It's surprisingly easy. I started with the idea of Mackay sketches, but I ended up pretty much with pre-sheaves, and used to have more complicated idea of what the signature for a theory should be, but now they're just any small graph. And structures are sets with the signature acting on the left. And for technical reasons, it's best to do it as using the idea of a discrete fibration. So a graph is as usual, and then the action is like is unique lifting, like in a discrete vibration, so that you're looking at the structure as being a graph homomorphism, so that historically this would be like the category of elements of the presheaf. But by actually doing a graph, having it be a graph with a graph homomorphism with unique lifting, you get around some technical issues about smallness. But still, it ends up to be like your intuition that an A object goes, and that is a signature object, which you're thinking of like a sort. It goes to a set, namely the fiber, and the arrow goes to that is an. Yeah, in the signature graph, you're thinking of the objects as being like sorts, and the arrows as being like dependencies, and these dependencies will go to an action, by the unique lifting. Then an entailment in a structure is, all right, well, it's an entailment is just a bunch of syntax using the graph. It's you have declarations. You're saying a variable has this sort, and then you have constraints that assuming you have these variables declared, then you have paths from them that meet, that you want to be able to define an equational constraint. And then an entailment then is an abstraction of a Horncloths. This has to do, I'm just talking about strong modeling, and there's also weak modeling where I would drop this. And then the premise is a bunch of these where the variables have to be declared and these paths have to be well sorted. And then the conclusion adds additional ones so that the premise actually is a finite presentation of a structure, because you have to actually get a structure, you have to close it up under the action by the graph, by the signature. And when you add on the conclusion, then that's presents another graph, and then the entailment actually presents a map from here to here plus here. Yeah, and then you're modeling declarations by elements, and then constraints by equations in the structure. And then a model, because I mentioned that you can actually look at it as an arrow within a model. That's actually means it's orthogonal to the arrow. That is, when you have a structure and you have an arrow from the premise to the structure, then it uniquely extends to the premise plus the conclusion. And so categories can be presented using or specified using entailments. You start with a graph for two simplicial sets, where you have a sort for objects, a sort for arrows, and a sort for triangles, and then you have the face and degeneracy operators. Then you need simplicial entailments, so that these, when you have an object, then you get the appropriate simplicial equations.
When you talk about triangles, is that really basically compositions?
Yeah, exactly.
Okay.
So when I want to composition, then I say when I have arrows that are composable, that there is a triangle with the right face operators. And then to make entailments are really low level. They're kind of like an assembly language. So it's nice to have functional sugar where you actually have a composition function, and then that makes it easier to write down what associativity is. And then, the last of what I want, there's a notion of folding where you take an entailment and push it out along itself and form the codiagonal, and then that's the folding. And then essentially an Atomic and Rizicki thing is that so weak modeling is just injectivity, that you can just that you can extend a modeling of the premise to the modeling plus the conclusion, but you can, if you weakly model both the entailment and its folding, that's the same as strongly modeling the entailment. And the reason why that's important is that once you have folding, if you have a bunch of entailments as axioms, a small set of entailments as axioms, you can close that up under pushing out along finitely presented structure arrows. And then also you close it up under identities and composition. Oh yeah, but yeah, first you close up the axioms under folding. That's crucial. And then the push out is like well, instances. And then yeah, so then when you have this notion of deduction, you can actually say what the initial model is, and that if you had a structure presented by a premise, that you can represent this map by a fraction like this, where this is a deduction, and then this is a finitely presented structure arrow, thinking of answering this query. And then when you can put two of these represent the same arrow when they can be put over a common denominator. Okay, so I think I assume my time is up.
Yeah,
but, yeah. But this is what additional entailments for a primitive recursion look like.
Okay. Anyways, Jim, thank you very much. We're going to have some questions now, and then I'm going to shut off the recording, and we'll have even more questions. So,
okay.
Any questions? Okay. Okay. So we're gonna shut off. I just want, before we shut off the recording, I just want to say the next talk is on April 19th. Walter Tolan will be speaking, so please show up. Okay. So, anyways, Jim, thank you very much again. Hold on. We're gonna stop the recording.